So, first of all, my apologies for Wednesday. It was amazingly stupid mistake with planning on calendar. I still don't know how I could make this, but I made it. It happens. So hopefully people who cannot attend will watch the video and they will catch up on what we do. Also, Professor Sherwin asked me that he follows the book, so I will try to enforce myself to stay as close to the book as possible in order to make it substitution comfortable for you guys. So we will talk about energy today, about potential energy, and as far as I understood, you pretty much covered everything, including section 5.3, right? And in section 5.3, you calculated some examples of work, and including some examples of work that is path independent. Does it tell you something? Is it clear? Awesome. So first thing that I should stress your attention to is that if you have initial point A, final point B, and you could move object from point A to point B in a variety of different ways, whatever your creative brain could make, then there are some forces for which, if you calculate work, Poplar and Kolonkov uses this notation C, contour integral. Make sure that you understand the difference that contour integral, this is letter C. It is not the same as closed path integral. It is completely different notation, and I saw people mixing this with each other. So these are absolutely different things. More conventional is to write integral and write contour C, but they use this convention. Let's follow this convention. So contour integral from RA to RB means this contour C starts on A and ends on B. Is path independent? And if it is path independent, F dot dr, then it is change of some kind of function that knows only about A and knows about E. So it is some kind of phi final minus, or I can say phi in RB minus phi in RA. Does that make sense? So it could build, we could build some kind of function like that. Do you need an explanation for that? I could explain more about it. Yeah, let me explain more about it. So why this is true. But idea of path independent is clear, right? You did it last time and you got it. Awesome. So what if I doubt? Oh, no, maybe it is not phi of RA minus phi of RB. How could we do that? How could we do that? Let me try. If I have point A and point B, let me also select point 0. Got it, right? Alright, so how could I go from point A to point B? Because work is path independent, I can go from point A to point B any way I wish. Alright, let me make my way this way. All the way to point that I call 0, and then from point 0 to point B. Why not? If all paths return exactly the same answer, sure, I can do that. So, let me say that work from A to B is now split into work from contour going from A to 0 plus contour that going from continues from 0 to B. Sounds good? Amazing. Then what I can do, if you go from A to 0 and then from 0 to B, can I say that if I calculate integral from A to 0 or integral from 0 to A, what can you tell me? please compare these two integrals. Integral from a to 0 of f. No, you understand that I was lazy. Let me be less lazy. F dr. F dr. F dr. Alright? Yeah. And this bar means vector, I'm just lazy. Yeah. So if you calculate f dr from a to 0, and if you calculate integral f dr from 0 to a, what can you tell me about these two integrals? Yeah?
Won't be negative of the other.
Exactly. Because if I did not change force, and instead for step delta r, I made step negative delta r. Alright? No absolute value change. Yes, sign change. Correct? It means that my integral from a to b f dr could be written now this way. Let me write this first. From 0 to b f dr, and then minus integral from 0 to a f dr. What I just did, I built function phi. If I define, let me call this work from a to b. If I now make definition, phi of Ra is called integral from 0 to a f dr. Then what is this? And you know what? Let me tell, like, just whatever r. And I was lazy with writing AB instead for RA and RB. Let me be less lazy, even if I need to be less lazy. Let's talk like I did there, right? From RA to RB, from 0 to RB, from 0 to RA. Ooh, yes. Yeah, help. If you got this definition, I just defined this function. Then what can you tell me about this integral? Looking at this definition. Any wild guess? Once again, what is phi of r? It's kind of new function. I just introduced it for you. How it is defined? You need to integrate given force all the way from point that I love, I call it 0 point, to given point r. Now, if integral is f dr from 0 point to point rb, then is this integral same as that? If you treat r as r, is it clear? What is this r? Any point in the universe. If I apply this definition given for any point in the universe, particularly for RB, okay, my final destination point became well defined. It is RB. Is it clear? So what I just proved, that work from A to B actually could be presented as phi of RB minus phi of RA. Does that make sense? You don't need to do this proof. K&K kind of takes it for granted. It says since work is path independent, it could be presented as this kind of difference. Honestly, here is proof. More convincing. Question?
This is only for like conservative forces though, right?
Good. So let me call it that way. Only for path independent integral forces. In a couple of minutes we will call them conservative. Make sense? Or potential. There is little difference between conservative and potential forces if there is time dependence of forces. But if you have static force like gravity today and tomorrow is the same. Alright, so Coulomb's law doesn't change on day-to-day basis. If there is something time dependent, then there is difference between conservative and potential. In physics 103, you will see that little difference. Today it doesn't make any sense to talk more about it. We good? Alright, so for some reasons that will be clear in 3-4 minutes, so not sometimes in the future, today. For some reasons, this is good to do what? U of r whole negative phi of r. It looks like I try to make things difficult. Soon you will see why this minus is so cute, okay? Alright, so let's see cuteness of the minus. To see cuteness of the minus, first of all, let me make a statement right here. So if work is equal to phi final minus phi initial, which is delta phi, then with this definition, work from A to B is equal to what in terms of U? Exactly, because what is difference between phi and U? Minus. So this is negative delta phi. I'm happy that we described this here, and I'm happy that K and K did this transition. What do they call this function? Just function of R. I call it phi. What they write explicitly, function of R. I call it phi. And good that they explained that, because sometimes it sounds like magic y minus. Answer, because I want so. Alright, why do you want so? 5 minutes and it will be clear. So far so good? Awesome. Any questions? Please.
Did you mean to write phi for both of those? Because you defined W equals delta phi and also...
See, that's stupidity. I just said that this is U and I wrote phi, which is total stupidity. Thanks, good catch. Awesome. People who took classes with me know that I made some typos, because I never teach from slides, I always teach from the board, and downside, sometimes typos, but you need to catch those. And I will see all those as soon as I will apply it. I will see them, but better if we catch it. So far, so good. Alright, so let's move on. Moving on, let me make sure I don't miss anything important. Sometimes earlier, you definitely proved work energy theorem, did you? Or more specific, work kinetic energy theorem. Now it clicks with everybody. What this theorem tells you, if you have all forces work from A to B total, net force, total force, all forces, whatever, it is equal to K final minus K initial or delta K. Now, to be consistent with my previous notations, let me call it RB, let me call it RA, which is delta K. Sounds good? Does this theorem require forces to be path independent? Work and kinetic energy theorem. No is right answer. Let me quickly remind you. You get this theorem from integration of MA. That's it. All you need to do to get kinetic energy is to integrate MA. Make sense? What is MA?
Force.
Net force.
Oh.
Is it necessarily potential force?
Oh, no.
F equals MA for any forces. Friction forces, potential forces, Lorenz's forces, even if you have no clue what I just said. Lorenz's force. Does that make perfect sense? Awesome. So, let's move on. Item 4. What if all forces in the system are path independent? Then what? I don't know, my spelling is not the best. Sorry, my writing handwriting. If all forces in the system are path independent, then what? Help? Please.
But then the total work is the change in potential energy?
Almost right. Oh, negative. So then, if all forces are path independent, then total force from A to B is not only equal negative K, total force from A to B is also equal to negative U. Interesting, right? Only if all forces are potential. If all forces are not potential, then second statement is not valid. Is it super duper clear? And if that is super and also duper clear, then from here we can make conclusion that delta K is equal to negative delta U. Alright, could I move U to the left side? Then what I'll get? Delta K plus delta U equals 0. And what is delta K plus delta U? Aha! This is delta of K plus U. And if change of something is equal to 0, then what? If something does not change, then what it is? Constant. So we got that K plus U is constant. What it is called? Conservation of energy. So now let me ask you, what if we did not introduce work as negative delta U and left it as delta phi? Then what conservation of energy would look like? Help?
K minus U?
Exactly, it would be K minus U. Is it bad? No, it's alright. But we will have some strange thing. Conserves difference. Let's say conserves sum. Ooh, yeah? You see different? So it's, what is it? Aesthetics. We just want to say total energy is equal to sum of kinetic plus potential. Sounds awesome. Saying that conserved value is equal to difference sounds like what? Makes sense. It's just nothing but beauty. Awesome. So what we just did, we introduced concept of total energy, and total energy is defined as kinetic plus potential. In case if all forces are potential, then this is true. By the way, maybe at some point later you will learn that. Let me write something really quickly today, and at some point you will learn it in more details. If all forces are potential and not potential, then what? Help? Let's say, for instance, there is gravity and air resistance. As object drops, gravity does path independent work, resistance does path dependent work. Life is complicated. So, could you tell me something about this? Say something crazy. I mean, when I ask, what could you tell me? What can I write right now?
Is not equal to 0.
Yeah. Be more specific. Could I write something? Well, I will write equals and write something smart. Please help. Say, don't worry, say total stupidity. It's totally fine. It's cute. Go.
I mean, that would be inequality. That would be smaller than the initial energy of the system.
Small. I would write something equals and would write equation. And guess what? Since I ask you, you can answer it.
That means
Moreover, the equation is somewhere on the board.
k plus u plus fx.
Okay, what are you talking about? Do you want me to sub something here, something there?
Wait.
Don't be afraid, yes.
Negative delta u is equal to
This negative u, or this is negative u, or this is negative u?
left side.
No.
Potential
Raise hand have priority. Other than that, I'll give yelling people 1, 2, 1.
The middle term is delta U.
Aha! Almost.
Negative.
Negative delta u. See, work of potential forces is equal to negative delta u. Amazing. What else you could say? Yes?
The left term is delta K.
Awesome. Work of all forces is delta K. What can you say about this term?
Oh, it's
No.
no.
More ideas? Please?
I was gonna say it's just equal to kinetic.
No?
It's
No? No? Let me keep intrigue for a couple more seconds.
counter.
No?
Just leave
No.
it out in.
Oh! Exactly. Answer is nothing. Okay? Alright, so now what we can do? You could move this to the left side, and you got delta K plus delta U, which is delta E, and it is equal to work of not potential forces from A to B. So what is that? Unlike the law of conservation of energy, this is law of dissipation of energy. So if there is friction force, then total mechanical energy does not stay the same. Duh. Right? Right. Just to respect history, I want to tell you a couple of things. First statement. Isaac Newton, who built mechanics, had no clue about energy. Isn't that cool? Right answer is yes, it is. Second statement. Conservation of energy was not discovered in mechanics. Do you know where it was discovered? Huh?
Special relativity.
No, I wish, but not that late. Good try.
Electricity.
Huh?
Electricity.
Not really. Good try. Any more wild guesses? Yeah?
Chemistry.
Yes. It's such a shame chemists discovered something for physics. I mean, we have to take that shame. Yeah, apparently, do you know who discovered conservation of energy? It's kind of important thing, right? Yeah, good. So good to know who discovered conservation of energy. You maybe even don't know the name of the guy. Robert Meyer. I would recommend you to Google and find in Wikipedia there is long story about Robert Meyer. He was absolutely amazing person, had really tough life with some family tragedy, and even was placed in crazy facility, maybe for discovery of energy, maybe for something else, I don't know. Joule discovered conservation of energy as well without knowledge of Meyer. So that was not cheating, nothing unethical. Joule did same experiment as Meyer. Experiment was about stirring water with some kind of device, something that stirs water. And as you stir water, for instance, making here some pulley and weight going down, you could measure what energy dropped when pulley was moving down mass m, and how temperature changed inside this container, and you can find out transformation of energy from one kind to the other. Yeah.
Joule should have an E, right?
Say it again?
Joule.
Maybe, you know, I'm not the best speller. Thank you. I always ask you to double check my spelling. I am not the best. Maybe the worst. What is his first name? James? Joule's first name.
I just looked up Joule and Meyer, and it was Martin Joule, Meyer and Joule. It's just the thing I'm reading.
It doesn't say first name, whatever. Yeah. Robert Meyer, I definitely know, because he was actually first. There is famous relationship in thermodynamics, Cp minus Cv equals R. It is also something what Robert Meyer discovered as Meyer's relation. But read about it. It's really good to read about history. But isn't it awesome that Newton had no clue about energy?
It's James Joule.
James, okay. James Joule. But as you can see, after it was discovered for thermal phenomena, people revisited basis of classical mechanics. This doesn't require any chemistry. It is based on F equals ma, period. And they discovered that this conserved value follows from the rest of classical mechanics. That is really amazing. So sometimes such discoveries are done in such indirect way. Oh yeah, one more thing that I need to mention here is the following. It is pretty clear statement, but let me make it. If I measured potential energy and have amazing function, but I decided to add to this function constant, would this new function be also potential energy? Yes. Why?
Because you get to choose where you set your zero.
Yes, but that's second statement. First statement, I should convince myself that this is true. Look, potential energy is discovered through change. If you subtract final potential energy in old definition minus initial potential energy in old definition, and you add to both exactly same number, when you subtract them, would that be any different? That means that because the definition requires change of u be equal to work, then if you add arbitrary constants, as you learned in Math 3b, when you integrate, we could add more arbitrary constant and it will be also antiderivative. So the same idea. Make sense? So this is called additive constant, and this is potential energy is defined up to additive constant. In mechanics, it is trivial statement. You might find such similar thing when for certain physics parameter is defined up to some addition, multiplications, a shift, in more interesting ways expressing themselves. Right now it is alright, whatever. And going back to students' interpretation, you could select zero level wherever you wish. If instead for point what I call zero, then at that point location, at this location, I will select zero somewhere else. It will just change my function phi, and because u and phi are defined through each other, that will change function u, but it will not change function delta u that is supposed to be related to energy. 7, 8. So maybe I'll write 8. What I just said, I will maybe write. So you could then turn around and after all these manipulations that we did, you could make a statement that potential energy is called such function that satisfies the following: work done from A to B is equal to negative delta U. So whichever function satisfies this definition is called potential energy. Right? It's just quick summary of everything what we did. You could also write this in infinitesimal fashion. FdR is infinitesimal work. Negative du is infinitesimal change of potential energy. These two definitions are equivalent. One is in integral form, the other is in differential form. They both are same useful. Any questions? Yeah.
For 7, was that only for path independent functions?
Whenever you use U, it means you deal with force that is path independent. And maybe going back to students' question about conservative forces, if force has path independent work, only under this condition we can find conservation law. So because of conservation law, that force is called conservative. Make sense? So that means that partial path independent or conservative, for us it is the same. Later you will learn these forces are called potential. If there is such potential function whose negative change is equal to work, and if potential is time dependent, it stays to be potential, but there is no anymore conservation of energy. Could you imagine that G of Earth is changing? Oops, there will not be conservation of energy. Thank God G does not change. As soon as it will change, we will find a refuge for ourselves. We will hide in shelter. Okay, any questions? Are we all good? Awesome. Since I said about G, let me remind you that force of gravity is mg. Wow, okay. So if I select y-axis going up, then if I do dr, what is dr? It is dx times I plus dy times j plus dz times k. Did I surprise anybody? It's trivial, right? Good. Then could you please tell me, if you dot multiply this mg by this dr, what is g dot I? Good. What is g dot j? Negative 1. Sorry, negative g. So mg times dyj will be negative mg dy. Is it super duper clear? Awesome. What is k times g dot product? So everything what is perpendicular, dot product is 0. Awesome. And that should be equal to negative du according to our differential definition of potential energy. Isn't that good? Alright, so what we do, we just look at this part and integrate it. So what happens to minus? It is on both sides. By minus. Alright, so we got that u is equal to mgy plus constant. So therefore, if I select u equals 0 at y equals 0, then u equals mgy. Or mgh, whichever way you want. But that comes with this choice. Any questions? No questions. Maybe it is good. Maybe it is not good. I don't know. Let me see. Yeah. Couple of applications. When energy is conserved, and it is conserved if we deal only with conservative forces, it makes easier to solve some problems. For example, if you got pendulum and you want to derive equation for pendulum oscillations, you could deal with forces T force, mg force, then get rid of T force, and then finally write equation. Yeah, works. However, you can also set up total energy of this system. Oops. Total energy is equal to potential plus, let me start with kinetic. Kinetic plus potential. Yeah, we know that. What is kinetic energy? It is 1/2 m, oops, it is mv squared. What is potential energy? mg y. All right. Let me see where I want to select 0 y. I actually don't mind. Let me do it slightly different than k and k. Result is the same. So if this is y-axis and this is 0, right? Then, and length of the pendulum is L. All right? Help me. What is speed? Because velocity, absolute value is speed, right? Instantaneous. So what is speed of this point?
The angular velocity times L.
Awesome. Angular velocity multiplied by the radius of that circle, which is L. Amazing. Is equal to 1/2 m L omega. Okay, I don't want to do this. What is omega in terms of theta?
Theta L.
Awesome. All right, thanks. That simplified one line. And don't forget square that I was about to forget. What about mgy? Yeah, okay. What about mgy? What is y of this point? If this is direction of y and if this is 0. Awesome. So mg stays. Y is negative L cosine theta. Amazing. Questions? And now, look, first of all, big advantage comparing to Newton's second law. I was not messing with T force. I didn't need to get rid of T force. I just don't want T force. It does not help me. It is not part of energy by T force, right? Amazing. Second, if I know that there is conservation of total energy, and it is total energy, could you guys help me? What is derivative of constant?
0.
Beautiful. Derivative of this expression should be 0. Yay? Yay. Let's find derivative. 1/2 m. What is derivative of square function? 2 times
L
theta dot. Am I done? No, because I'm doing derivative with respect to t, which means I deal with
Oh,
what?
time. Well,
Chain rule.
Oh,
I just differentiated square. Now I need to differentiate whatever is inside. What is it?
L theta dot.
L theta dot dot. Awesome. Chain rule, math 3a, yay. Good. We're done with first term. Second term, minus mgl. What is derivative of cosine?
Omega. Negative.
First of all, negative sine theta. Are we done? Now we should multiply by theta dot. Amazing. What did we say about derivative of energy? Fantastic. So derivative of this is 0. Beautiful. Let's check out things. First of all, do we care about masses?
No.
They're everywhere. Second thing, do we care about theta dot? It's everywhere. Simple thing. More colors. What about 2 times 1/2? It's awesome, right? Amazing. So, one more thing. What else? L. One of L's. The other one stays. So many things cancelled, right? That makes life easier. What is left over in this forest of cancellations? L and theta dot dot. Let me divide by L. So I got theta dot dot plus, because minus and minus is plus, right? G divided by L multiplied by sine theta, and that is equal to 0. This is equation of pendulum. This is called not linear pendulum. If you guys are interested to learn how not linear systems work, not this spring, but any spring in the future, after you will do a little more, after you will be done with Math 6b, take Physics 106. This class is called Not Linear Phenomena. It sounds difficult. Apparently one of the easiest upper div classes. This class is cross-listed with ME and ECE. ME 169, ECE 183, or other way around. I forgot which number, doesn't matter. And usually physics students get best grades. When I taught this class, I uploaded grades and then I hit my head. So all ECE and ME were like from F to C plus. But overall, this was good. And then I uploaded by, yeah, sorry, it's not politically correct statement, but it's alright. The only reason is not to make fun, because if you take hardcore engineering, you will get all maybe bad grades. But the thing is that it's not difficult class. By the way, Professor Sherwin was first who taught this class. He developed curriculum for this class. It's amazing. You could ask him more questions. He taught it more than I did because he was the very first and did it a couple of times already. You could ask him for more details. It's awesome class, absolutely. Now, if you do small angle approximation, then sine of theta is approximately equal to angle. We did it in Physics 8, and you did it everywhere else. So then theta dot dot plus G over L theta equals 0. That is classical simple harmonic oscillator equation, and there is no problem to solve it. Solution is sine and cosine of omega t. Any questions? Are we good? Amazing. I encourage you also to look in the K&K, how they deal with that. And I will do something else. I think I can erase all these things. Ten, right? 11. Let me do one more thing. If you have this kind of potential energy as a function of x, and let's say this potential energy somehow depends on x, not necessarily that beautifully. Okay, maybe that way. And let's say I have a point, XA, where I placed, what it means, this is the space, this is not, the actual space is here. Could you imagine, I have a string for instance, I placed mass bead on this string, and this mass can travel on this string. And mass, for instance, has some kind of charge, and I exert force that changes somehow the way that potential energy looks like whatever function. Is it clear? For instance, if this bead is on spring, potential energy will be kx squared over 2. You know about that, right? Kx squared over 2. Is it something you heard before? You're good, right? If not, I'll derive it. Do you guys need derivation of kx squared over 2? Yeah, I will do it because I don't need it. You know what? I'll do it. Okay, this is u of x, and u of x is often called potential well. Why it is called potential well? Because if you have actual landscape and potential energy is mgy, if you make landscape that follows y shape, right, then gravitational potential energy will behave like whatever profile you drew and asked me to dig the well of that shape. Make sense? It is not precise analogy, but really good one. What is not precise? If you imagine bead on this string, it travels in one dimensions, and as it travels in one dimension, for instance, mass on spring, potential energy changes that way. But if this is well underground, and I place here mass, it travels here, it actually travels longer path. See, this path is not same as this path. So when we say potential well, and imagine in our head that landscape has the same shape as potential, this analogy is not full, it's partial. Does that make sense? Is it good? Yeah.
What do you mean by well?
Actually, I can make profile of the floor, of the shape, as this exactly same shape as kx squared is u of x. Let me derive this kx squared so I will not be counterintuitive. And I will back to this picture in my next item. Item 12 is temporarily going back here. And here is x, here is 0, there is a spring, and you guys all know that Hooke's law, f sub x equals negative kx. F sub x is equal to negative kx. Everybody knows that, right? Hooke's law. Do you know what Hooke was famous for? What else he discovered? Something super important.
Microscope.
Yeah, he discovered microscope. Do you know what he saw? One of the first things.
Single-celled organism.
Yeah, he just not organism. He took cork, put it in the microscope, and looked in the microscope and saw that there are lots of cavities.
Oh.
And those cavities look like rooms where monks live. And rooms where monks live called cells. So he said, oh, I see cells. And then biologists started using something that Hooke invented, this terminology, because he invented microscope. Yeah, but his actual duty was to present new laws or new inventions bi-weekly for the London Royal Society. And if he could not find anything, at this time there were no journals, so he could find something, and if he couldn't, he was inventing himself something new. So there are about 400 laws that Hooke discovered just because of his duties, the secretary of the Royal Society. He was genius, and Newton hated many geniuses. He was one of those who Newton hated from the bottom of his heart. But let's not speak about him right now and move to this. I don't want to be annoying, and I don't want to write this again. I invite you to look at dr. dr is that. Okay? Imagine I wrote it again, but it's there. So, what is force? If I want to write this force in vector form, I'll write negative kx times I hat. Alright? Now I invite you to do dot product. This force, dot multiplied by I is, I is 1, but negative kx holds. What about I dot j? What about I dot k? Awesome. Which means that FDR is equal to negative kx. Also, FDR is equal to negative du. Amazing. Integrate. Oh, what I missed?
RDX.
Aha, so you guys need to see my, I told you eventually I will see my mistakes, but you better find it earlier. For practice reason. Alright, now I can say that, why not integrate this both? And why not cancel minuses? So what we get? U is equal to 1/2 kx squared plus 0. Did I say plus? Plus constant. But Zygmunt told me everybody selects this constant equal to 0, right? So usually people write that Hooke's energy is 1/2 kx squared. Now, if I have a string with bead sitting on this spring, secured to this string, and then this mass as it goes away from 0, so this is x-axis, and whatever spring is not stretched or stressed, I label that point 0. That's point of equilibrium, right? Then, if I decided to plot u as a function of x, it looks like I just derived 1/2 kx squared. So, bead on spring on string travels back and forth. At the same time, potential energy changes quadratically. It is similar, but not precisely, to the following situation. If I make a landscape of exactly same shape, so instead for just x, if I have x and y, Jesus, I did y and y. X and y. And if I will actually dig soil or make some kind of engineering construction that has this shape, what shape? If y is equal to 1/2 kx squared, then what is potential energy? It is mgy, which is mg times 1/2 kx squared. Alright, I don't like this mg here, right? Okay, let me divide this by mg. So then it will be over mg. Answer is 1/2 kx squared. So if I have an engineering friend, I will tell my friend, make please this shape. You know K of the spring, you know mass of the bead, you know G of earth. Calculate this coefficient and please produce this track, like skateboard track, alright? And ask a little insect skateboarder travel on that track. Then for this skateboarder, potential energy will change exactly the same way as for this bead. Is it clear? That's why shape of potential energy is often called potential well. There is no actual well, it's in our imagination, this little skateboarder insect on this kind of shape, but it's really cool similarity. What is not cool is that this, our little friend on skateboard, little bug, here, travels longer path than this bead. So their similarity is not complete. But Naine's potential will, intuitively, you could imagine that. It's really good for intuition. If you remember, there is no full analogy that path, that if you are bead on string, you travel along straight line, it's just your potential energy changes. And here you travel on curvy linear path, and your altitude is changing. When your altitude is changing, your gravitational potential energy is changing. That's the hint. Make sense? So this is beautiful word, potential well, but it is limited. If you understand the limitation, then you are welcome to keep using words potential well. Now you understand all story. So what I was going to do next, 13, I was going to explain something really cool. Look at this potential well. If you placed mass at this point, see, remember, this mass is in x space, like this bead is only on this string. So it's actually not placed here, it is placed there. This is the value of potential energy. So if you placed mass at point xa with velocity 0, then initially you have u of xa plus 0 kinetic energy. Make sense? For example, have in mind deviated bead that you hold with your fingers at point xa. And then you release it without pushing it. Right? What happens to the bead? It will be involved in motion by spring. So at an arbitrary moment, it will be sum u of x plus 1/2 mx dot squared. Follow this example with attention, not example, this theoretical construction, because K&K does exactly the same thing, particularly for pendulum. Solves that. So it's solved in the book. So then you will understand exactly what is going on if you follow me right now, and it's really easy to follow. So look at that. I can subtract u of x, multiply by 2, divide by m. This is algebra 1. Can I do all this in once? Thanks. So then x dot square, remember I said square, I didn't write square, is equal to what? Imagine that this is still square. Then what it is equal to? Yeah.
V squared,
Say again?
V squared, like velocity squared.
Imagine I wrote here square. Okay, let me temporarily write square. I will soon erase it. So far it is square. What it is equal to?
UXA minus UX.
Good. Or 2 over
2 over
m, parenthesis, brackets.
UXA minus UX.
Isn't that trivial? It's like algebra 1. I subtracted ux, then I multiplied by 2, then I divided by m, and I got x squared. What if I don't want x squared? Then I should put here radical. Not that bad, right? Awesome. Now let me complete the thing. To complete this thing, I will do